Today we shall study about the validity of ray optics in wave optics. An aperture slit or hole of size illuminated by a parallel beam sends diffracted light into an angle of approximately lambda by a. This is the angular size of the bright central maximum. In traveling a distance z, that diffracted beam acquires a width z lambda by a due to diffraction. It is interesting to ask at what value of z the spreading due to diffraction becomes comparable to the size A of the aperture. We thus approximately equate z lambda by a with a. This gives the distance beyond which divergence of the beam of width a becomes significant. Therefore, z barabar a square by lambda dash 1. We define a quantity Zp called the Fresnel distance by the following equation: Zp barabar a square by lambda. The equation shows that for distances much smaller than Zp, the spreading due to diffraction is smaller compared to the size of the beam. It becomes comparable when the distance is approximately Zp. For distances much greater than Zp, the spreading due to diffraction dominates over that due to ray optics. It means the size of the aperture. Equation 1 also shows that ray optics is valid in the limit of wavelength tending to 0. Now, polarization. The figure 1a and b shows the graph between displacement and time. Now we explain the polarization. Consider holding a long string that is held horizontally, the other end of which is consumed to be fixed. If we move the end of the string up and down in a periodic manner, we will generate a wave propagating in the plus x direction. Such a wave could be described by the following equation: by function of x t barabar a sin kx minus omega t, where a and omega represent the amplitude and the angular frequency of the wave, respectively. Further, lambda barabar 2 pi by k represents the wavelength associated with the wave. Since the displacement which is along the bidirection is at right angles to the direction of propagation of the wave, we have what is known as a transverse wave. Also, since the displacement is in the bidirection, it is often referred to as a bipolarized wave. Since each point on the string moves on a straight line, the wave is also referred to as a linearly polarized wave. Further, the string always remains confined to the xy plane, and therefore it is also referred to as a plane polarized wave. In a similar manner, we can consider the vibration of the string in the xz plane, generating a z polarized wave whose displacement will be given by z barabar a sin kx minus omega t. It should be mentioned that the linearly polarized waves are all transverse waves. It means the displacement of each point of the string is always at right angles to the direction of propagation of the wave. Finally, if the plane of vibration of the string is changed randomly in very short interval of time, then we have what the string is changed randomly in very short interval of time, then we have what is known as unpolarized wave. Thus, for an unpolarized wave, the displacement will be randomly changing with time, though it will always be perpendicular to the direction of propagation. Light waves are transverse in nature. It means the electric field associated with the propagating light wave is always at right angles to the direction of propagation of wave. This can be easily demonstrated using a sample Polaroid, we must have seen thin plastic like sheets which are called Polaroid. A Polaroid consists of long chain molecules aligned in a particular direction. The electric vectors along the direction of the aligned molecules get absorbed. Thus, if an unpolarized light wave is incident on such a Polaroid, then the light wave will get linearly polarized with the electric vector oscillating along a direction perpendicular to the aligned molecules. This direction is known as path axis of the Polaroid. Thus, if the light from an ordinary source like a sodium lamp passes through a Polaroid sheet P1, it is observed that its intensity is reduced by half. Rotating P1 has no effect on the transmitted beam and transmitted intensity remains constant. Now let an identical piece of Polaroid P2 be placed before P1. As expected, the light from the lamp is reduced in infinity on passing through P2 alone. But now rotating P1 has a dramatic effect on the light coming from P2. In one position, the intensity transmitted by P2 followed by P1 is nearly zero. When turned by 90 degrees from the position P1 transmits nearly the full intensity emerging from P2. The above experiment can be easily understood by assuming that light passing through the Polaroid P2 gets polarized along the path axis of P2. If the path axis of P2 makes an angle theta with the path axis of P1, then when the polarized beam passes through the Polaroid P2, the component E cos theta will pass through P2. Thus, as we rotate the Polaroid P1 or P2, the intensity will vary as I barabar I naught cos square theta, where I naught is the intensity of polarized light after passing through P1. This is known as Moul's law. Polaroid can be used to control the intensity in sunglasses, window planes, etc. Polaroids are also used in photographic cameras and 3D movie camera. Polarization by scattering as shown in figure A and B. The figure 1A shows the incident sunlight is unpolarized. The dots stand for polarization perpendicular to the plane of figure. Under unpolarized, the dots stand for polarization perpendicular to the plane of figure. Under the unpolarized, the dots stand for polarization perpendicular to the plane of figure. Under the influence of electric field of incident wave, the electrons in the molecular acquire components of motion in both these directions. We have drawn an observer looking at 90 degrees to the direction of sun. Clearly, charges accelerating Polaroid to the double arrows do not radiate energy towards the observer. Since their acceleration has no transverse component, the radiation scattered by the molecule is represented as no transverse component. The radiation scattering the molecule is represented by dots. It is polarized perpendicular to the figure. This explains the polarization of scattered light from the sky. Polarization by reflection. When unpolarized light is incident in the boundary between the transparent media, the reflected light is polarized with its electric vector perpendicular to the plane of incidence. When the refracted and reflected rays make a right angle with each other, thus reflected wave is totally polarized wave. The angle of incidence in this case is called Bristol angle, denoted by IV. Now by Snell's law, mu बराबर sin IV बटा sin R बराबर sin IV बटा sin pi by 2 minus IV बराबर sin IV बटा cos IV बराबर tan IV, known as Bristol law.